Okay, we're looking at a problem from section 2.3, an application problem involving velocity. And they say here the height s in feet at time t in seconds of a silver dollar dropped from the top of the Washington Monument is given by, okay, and here's the formula. So if you tell me the number of seconds, which is t, that the silver dollar coin has been falling from the Washington Monument, I can tell you what its height is. Now this question asks a few things about velocity. So first of all, you'll notice in part A they ask for the average velocity on the interval 2 to 3. So what they're asking for is, what's the average rate of change of this function between the second of the drop and the third second of the drop. Well, we have that formula for the average rate of change in the book. We just take the difference in function values, so s of 3, the height after 3 seconds, minus the height after 2 seconds, and divided by the change in time in this case. Well, and to compute this, we have to put 3 into this function for t, and 2 into this function for t, and take the difference there. So we'll go ahead and do that real quick. Okay, so after 3 seconds, the height is 411 feet. After 2 seconds, the height is 491 feet, which looks a little strange, but that is the way it works. It's going to be further down after 3 seconds than it is after just 2. And we divide that by 3 minus 2, and we get negative 80. So what is that? Well, that's the velocity of this object in feet per second. Now, when velocity is negative, we usually interpret that as downward movement. So, in other words, the average speed of this object between the second and third second of its drop is 80 feet per second down. Okay. Now, part B asks for a little modification here. They ask for instantaneous velocities at 2 seconds and at 3 seconds. Okay. Well, again, that's that's something that requires the derivative. The instantaneous rate of change is given by the derivative of this function. So what we really need to find to answer part B is the derivative of s with respect to t. Okay. So we could also call that s prime of t. Really, this is s of t as a function, so let's find its derivative. Well, we just need to take the derivative of the distance function, the height function, and we can use our derivative rules now. So first of all, I can use the sum rule. I can take the derivative of each term separately. So I'll take the derivative of the negative 16t squared and add to that the derivative of 555. Okay. Now again, to save a little bit of writing, I like to do some of these rules more than once, more than one rule at a time. But the next thing I would do to compute this derivative is factor that negative 16 out front. Okay, because in this term now I just have negative 16 times t squared. Well, the constant multiple rule says I can factor that out front. Okay, so I get negative 16 times the derivative of t squared, which is 2t, plus the derivative of 555. Of course, the derivative of any constant is 0. Okay. So what I get here is negative, let's say that'll be negative 32t. Okay. So that gives me the velocity in feet per second at any time, the instantaneous velocity. Okay. Now, just to kind of tuck it in here so we can keep everything on the board, they did ask us for this velocity after 2 seconds, so I can substitute 2 in for t, and I get negative 64 feet per second. So after 2 seconds, this coin is dropping negative 64 feet per second. Now, of course, I can also find the velocity after 3 seconds. And if you know how things move when they drop, they tend to accelerate. They're going faster and faster as time moves on. So after 3 seconds, this velocity will be an even larger negative number. Okay. And of course it is. If we put 3 in for t, we get negative 32 times 3, which is negative 96 feet per second. Okay. So we computed 3 velocities here. At 2 seconds, this coin was dropping at exactly 64 feet per second. And its velocity was exactly 64 feet per second downward. At 3 seconds, it was exactly negative 96 feet per second. So 96 feet per second downward. Okay. However, in Part A, we did something a little different. We found the average velocity between its second and third second of travel. Okay. So, an example of both average rate of change, which is just an algebraic formula, it's like computing the slope of a line, and instantaneous rate of change, which requires the derivative.